Okay, so good morning. Today we're going to be looking in a little bit more detail at some trigonometry. We've already talked a lot about sin, cos and tan and indeed the sine and cosine rule, but I just want to go into a little bit more detail about those functions in particular and how we can use our understanding of those functions to sort of maybe just get a little bit more of a grip on what exactly we're doing. Okay, so we're going to just have a little look at some stuff on my whiteboards to start off with. Initially, I just want us to consider these three triangles. Now, just quickly before we start, sin, cos and tan are actually shortenings of the words sine, cosine and tangent, but we do tend to just use those shortened versions when we discuss trigonometry. We are familiar, however, with SOHCAHTOA, so you can see here for a right angle triangle, when we're using the sine function, we've got the opposite and hypotenuse, cosine adjacent hypotenuse, and tangent, we've got our opposite and our adjacent sides. We should be very, very familiar with that idea of using SOHCAHTOA. So moving down a little bit, if we consider a couple of sums, let's say, I've just plugged in a few random numbers here, we had a sum which was trying to find an angle. And we would therefore, if we're using the sine function, we'd have the opposite over the hypotenuse. We'd say sin theta equals 4/5. And the next step is really, really important. The one I want us just to make sure we've got a good understanding of. We would take the inverse of our sine function to work out that angle. Okay, so to work out an angle, we're going to use the inverse function. In contrast, when we're working out a length, I'm using the cosine as an example here. To work out the adjacent length for a cosine, we'd do the cos of the angle multiplied by the hypotenuse. You can see that's what I'm doing here. And you can see that we're just using the function in its normality as opposed to when we're finding its angle in its inverse form. Okay, so this is our trigonometry so far for right angle triangles. We should have a really, really good understanding of what that looks like. So just putting that to one side for 1 second, I want us to have a little look at the graphs of these functions. So I've started off just with two, the graph of the sine function and the graph of the cosine function. Now, a few similarities just for us to start off with, and guys, we need to be able to draw these two functions really, really well and get a good understanding of these. Firstly, obviously we've got our x and our y axes for both graphs. A similarity here is that the y-axis only ranges from -1 to 1 for both sine and cosine. Okay, in its simplest form, without any transformations, it's only going to range from 1 to -1 for sine and cosine. At this moment in time, for the x-axis, I've plugged in values from 0 to 360 for both of these. We'll talk a little bit more about extending that in a minute, but for now, let's just focus on that range. Now, there are 5 points which I think we really, really need to get to understand today on these functions. Firstly, for the sine function, clearly it goes through 0, 0. In contrast, when x is 0 for cosine function, y is actually going to equal 1. Okay, so there's a little bit of difference. In reality, these two curves are identical. Okay, in terms of the gradients, in terms of the shape, these are identical curves. What's happened is they have been translated slightly in the x direction, just moved in the x direction. Okay, these are identical curves apart from the values which they actually pertain. Just plugging in a couple more values. Let's say x was 270. On cos, that means that our y value would be 0, doesn't it? Okay, but in contrast, for our sine function, if x was 270, our y value would be -1. Okay, so we need to be able to read off the 5 crossed points which I have written onto those two graphs. Okay, 0, 0, 91, 180, 0, 270 -1, and 360, 0 for sin, 0, 1, 90, 0, 180 -1, and 270, 0, and 361 for cosine. Okay, so we need to be able to read off those coordinates of those points. Now, obviously, unfortunately, we do have a third function as well, and this is where we introduce our tan function. Now, clearly, just visually, this looks quite different to the other two. Okay, again, though, I have written 0 to 360 just for now for our x-axis. Big difference here is that I have not written 1 to -1 on our y scale. Now, that's because actually our tangent function can, in its simplest form, take exponential values, huge values, for certain x inputs. Okay, so we're not going to restrict its y domain in this instance. Okay, it's going to be an infinite scale for our y-axis. Now, another interesting thing here is that in contrast to these curves, which are like perfectly smooth and perfectly joined up, for our tan function, there's a big jump from this point to this point. It's not joined up in any scale. Now, that's because, actually, we include for our tan graph, our tan function, these dotted lines, which are asymptotes, which I think is a word we have briefly encountered before. Now, what that means is actually this function, the tan function, is undefined for 90 and also for 270. As in, if you plug into your calculator tan 90, your calculator will tell you you've got a math error. It's not possible to do that sum, okay? Tan 89.9 will get you a value, and tan 90.1 will get you a value, but tan 90 is undefined, okay? So we've got asymptotes, which are in our tan function. So those are our three graphs. Sin and cos, nice and straightforward. The tan one just going to take a little bit more time to get our heads around, because it's a little bit different, but hopefully should be absolutely fine. Now, first things first, we need to master being able to draw those graphs. What we also need to be able to do is we need to be able to sort of plug in how this stuff, which we said was quite easy, links back to this, or how maybe we can use this to get back to those other sums. So let's just consider a few questions. Let's say we had sin 90. Now, sin 90, we would be using the normal function, let's say if we were using some sort of length. So this is useful potentially if we were finding a length in a question. But to find out sin 90, what I'd like us to sort of show, and we've sort of seen this idea on scatter graphs before, is actually the sort of way in which we're going to find out what that equals. To get sin 90, we trace up 90 until we hit our function, and we come across to our y-axis. And from our graph, therefore, what I'm saying is that sin 90 equals 1. Okay? Now, I suppose what we could say is, using the function normally, then we have gone from our x-axis to our y-axis. Let's think about a different question. Let's say I wanted to do sin to the minus 1 of minus 1. Now, here I'm using the inverse function. So, as opposed to going x to y, when we're using the inverse function, I think I'd like us to trace our journey y to x. So, from minus 1 all the way to my function is here, isn't it? And from there, I'm going to trace it up, and I'm going to get 270. Okay, and because we know that we're using that as an angle, we're going to say 270 degrees is our unit for our x-axis. Okay, so we can use this graph to work out different values of sin something or sin to the minus 1 something. Same thing, just a little bit quicker now. Let's talk about cos 45. Now, cos 45, 45 obviously would be halfway between 0 and 90. So what we would be doing is we'd be tracing that up to here and then across. Now, this is not an obvious value. It's not where I had one of my crosses before, is it? Okay, so we are still going to use our calculator here in this instance. We'll talk about exact values of trig later on, but for now, we're going to use our calculator. And so if we plug in cos 45, that will be able to give me an answer. Just quickly though, what are we expecting? Well, we're expecting it to be somewhere between 0 and 1, probably slightly closer to 1. So cos 45 equals root 2 over 2, there's its exact value. Yeah, 0.71 to 2 decimal places. Okay, fine. Same idea again. Let's consider maybe cos to the minus 1 of 0.5. Well, 0.5 is maybe, let's say, about here. And so if we go the other way, well, we're expecting a value here somewhere, aren't we? So again, somewhere between 0 and 90, closer to 90. Now, again, it's not an exact one for us. So we're going to do cos to the minus 1 of 0.5 equals for us a nice 60 degrees. Okay, so it wasn't one of our 5 obvious ones, but it has still come out nice and clean. But we're still using the principle of going x to y for when it's just a normal function and y to x for when it's an inverse function. Now let's just take that one step further to the tan graph briefly. And let's just consider tan 90. I just want to show you this one. Well, if we do tan 90 on our calculator, as discussed, it's going to be a math error. The reason being is because if we try and trace 90, it's never going to hit the curve because we're tracing directly up the asymptote, okay? It's undefined. It's not possible. Let's just do another one quickly. And this one's just going to pull out the idea that the y is more than 1 to minus 1. So if we did tan to the minus 1 of 2, we don't really know where 2 is, so let's just chuck in a number 2 on our scale here. But if we do tan to the minus 1 of 2, we can come out with a value of 63.43. Okay, so that's this idea, isn't it, of coming down here to 63.43. Okay, so using our graphs, we can actually work out different trigonometric values nice and quickly. Now, hopefully that's all made sense so far. There's one really, really important thing which I would like us just to discuss quickly, and that is this idea that these graphs are not finite. So at the minute, I have the domain, don't I, of 0 to 360 on the x. But what I'd like us just to sort of say, and I'm just going to try and rub out some of my working lines briefly. We'll just focus on sin for now because it's one which I've done my rubbings on. what I'd like us just to see is that obviously I have 0 to 360 currently. This graph actually continues. Okay, so if we have 360, this graph actually continues in this shape, this way. Now, let's just think about this as 90-degree intervals. So this point here, 90 plus 360, will be 450, and this point here, you've guessed it, will be 1. This point here, another 90-degree interval, will be 450 plus 90, so that's going to be 540. Down here, this will now be 630. And if it did make it back up, I've slightly run out of room, it would be 720. So it keeps going for infinity that direction. It also keeps going, sorry, one-handed drawing is not very good, for infinity in this direction as well. So let's just consider this, 90-degree intervals. This point here, where it's -1, will be minus 90. And the point where it's back to 0 will be minus 180. Okay, so we've got an infinite function here. Same for cos, same for tan. Now, what that means is if we consider another question, let's just do cos to the -1 of 0.5, for example. Yeah, cos to the -1, 0.5. We already spoke, didn't we, about this idea that we're going to get our first value. Okay, this is going to be where we're going to get our first value, this one here, whatever that is. Also, though, there's going to be a value here, a value here, a value here, and also a value here. So there are going to be infinite number of solutions for cos to the -1 and 0.5. Now, your calculator, when we did that, is going to give us one value. It's going to give us 60 degrees, which is this one, the first one which we've got here. Now, let's think if we can work out these other ones, because these must have an answer. Our calculator's not told us it, though, which is a bit of a problem. So let's just spend maybe 1 minute just considering that. Important thing about this curve is that it is symmetrical, okay? So because it goes 0 to 180 just all nicely above here, we should be able to work out what this value is. Now, if it was 60 degrees above 0 and it's symmetrical, this must be 60 degrees below 180. Okay, so if we plug in a number, I reckon that solution is going to be 120. Okay, let's do another one. 60 degrees above 0, so if we've got 360, 60 degrees above 360, I reckon this solution must be 420. 60 degrees below 540, I reckon that solution must be 480. Hard ones down here now, okay, but let's just consider it briefly. This one here, okay, is 60 degrees after minus 180. I think that is minus 240. Now, we can prove this, can't we, those solutions, by doing cos of that number, okay? So we're expecting cos 60 to be a half, which it is. Let's hope that cos 120 is... oh, sorry, not cos, we're on sin, aren't we? Sin 60, okay. Oh, that'll be y. Okay, sin to the -1, we've used the wrong function. Sin to the -1, yeah, rubbish. Sorry, guys, we're going to start that all over again, that little process. Made a bit of a mistake. Sin to the -1 of a half is 30, sorry. So it's not going to be 60 below 180, it's going to be 30, so that's 150, okay. 30 above 360, 390, 30 below 540, 510, and 30 below 180, 210. Sorry, I made a little bit of a mistake there. So let's try that again. If we do sin 30, we're expecting it to be a half, which it is. If we do sin 150, it's a half, which is good. Sin, I think we said 390, a half. Sin 510, a half. And the one which we maybe is a little bit harder, sin minus 210, still a half. So guys, it's really important that we understand that these functions are not infinite, and therefore that there is going to be more than one solution. Your calculator will tell you one solution, but actually there are going to be an infinite number of solutions to do these, okay? Now let's just say we were doing like a bog standard sum like these ones back up here. We would use the one which the calculator gives. We would use the first positive one in terms of completing our sum. But it's important that we understand that there are multiple values for these questions. Now, a little bit further down the line, we're also going to be asked to learn some exact values of some trigonometric sums. Now, you might have seen earlier, I think it was when I was using cosine, it gave me like 0.71, but it also gave me in surd form. Well, here's just a very short table. Eventually, we're going to need to learn these. Now, some of these are really, really easy. We already see these from our curve. Sin 90, we already knew as 1. Cos 90, we already knew as 0. tan 90 we already knew was not applicable. Okay, it's not possible to do tan 90. So these ones are really straightforward, but we are going to have to learn exact values for these other questions. Okay, so sin 30, for example, is a half, and interesting, that's the same as cos 60 as a half. Interesting, sin and cos 45 are both root 2 over 2. Okay, so we can see a few different similarities and differences between our exact trig questions there, but we are eventually going to have to learn those. So hopefully that's just sort of added a little bit of depth to our understanding of some trigonometry. Sorry about my mistake for the cosine. I should have been using sin, so that was a silly mistake. A little bit rusty, I'm sure you guys are as well. But guys, it's really important that you try and get your head around that and have a go at some questions from the textbook as well. Okay, so cheers. Let me know any questions.